All right, on to the next one. Looks like we're working on the. There we go. The OSD tiering discussion for fine-grained promotion units. Zhiqiang, I think, is how it says. Did I pronounce that right? I think so. But it was your blueprint. If you want to give us a little bit of an overview of what you were thinking, and then we can go from there.
Sure. Can you guys hear me?
Yes.
Okay. I like to talking some things about talking two ideas on cache tiering. But at first, let me show some data first. Wait a moment. Okay, can you see my screen now?
Hey, one simple comment here. I think I have seen out the data previously, right after last week's weekly performance meeting.
Okay. This is some test we did before on cache tiering performance. We did 4 cases. The first three are for cache tiering, and the last one is for without cache tiering. But we have 2 SSD acting as the journal. For the performance of all of these 4 cases are shown in the table in this chart. As you can see, without the cache tiering result, the write performance is about 1,000 IOPS. The read about 1,500 IOPS. And for the random, it is 1,200 IOPS. Okay. Let me first say the difference between with cache tiering, case 1, case 2, case 3. The case 1 is to we set the dirt ratio and the full ratio of the cache tiering so that we can hold all of the data in the cache tier, and we don't need to do flush, and then we don't need to do evict, and there is also no promotion in case 1. And in case 2, there is flash work, but there is no promotion. And in case 3, we have both of we have all of the eviction, flash, and promotion in case 3. And as you can see from the result, the case 1 result and the case 2 result is good compared with the without cache tiering result, especially for the read. But in the case 3, which we have promotions, we have flash and evictions, the result is very poor. It's about for the write, it is just 7% of the. No. It's compared with the without cache tiering result, it is just about 35%, and for the read, it is about 60%. Yeah, so the result for the case 3 is very poor. And
is this random reads across like uniform random reads across the full data set?
Yeah, 4K random read right.
Because that's always going to be slower because you're thrashing, you're promoting and demoting stuff because your cache is too small.
No, cache is not too small.
This is the case where the cache is big enough.
Yeah,
you need something like a Ceph distribution where you have like really hot data and really cold data.
Well, hang on.
It's just totally random.
When you say that cache is big enough, do you mean that it's big enough to hold the entire working set? Because if that's true, it should be the same speed as whatever the cache tier is. So what are you doing?
Yeah, that's case 1.
Okay, I see.
Okay, so case 3, it's a small cache.
Right.
You can refer to the detailed configuration in the following pages. We have added it to the backup set.
Okay. Okay. So I think that if the size of the cache tier in case 3 is smaller than the size of the complete data set, and you're doing random reads and writes, then it's always going to be bad. right? Like the cache never works if you have a uniform distribution of data across all of your data. It ideally wouldn't be that bad. It wouldn't be that much slower, but it's always going to be worse than just using your base tier because you're doing this useless work of putting stuff in the cache.
Well, hang on. So the best case scenario is that it's as fast as your backing pool, right? So is this 35% compared to the backing pool or compared to the SSD?
And compared to the base tier.
Okay.
Yeah, the base tier is the first column.
Yeah, in the base tier we have two SSDs as acting as the journal.
Okay, so Sage, then like if the cache has no overhead, then we would expect 100% here, right?
Yeah.
It would be as fast as the backing tier. So this is saying that this is just having the cache enabled, even if it doesn't help, costs you 65% performance.
Yeah.
Okay. That makes sense.
Yeah. So it would be better if it weren't so bad, but it's always going to be slower than the base tier.
Yeah, that makes sense.
Right. Yeah, because you're doing more work to cache it, and then you're gonna get your hit rate on your cache is going to be bad.
Yeah, that is because we don't have a real world workload, so we use the FIO to run the test.
Okay.
So in addition to the tests in case 3 that you did do, what would be interesting as well is to have a ZipF distribution with FIO, which would let you look at when you have a combination of hot and cold data, what kind of performance you see. My guess is it will still be bad, just based on the tests that I've done, but maybe it won't be quite as bad.
Actually, maybe that is a wrong question. So we're trying to figure out the overhead of cache tiering, right? That's me. I'm going to put on headphones.
All right. It looks like FIO has support for ZipF now.
Yes, we have.
Yeah.
We do have some data on that, but yeah, so it's
better.
Not too hard to do it.
Yeah. Good suggestion. We can try this later, I think.
Okay.
And this is the ops data. We can also look at some of the latency data. As it is shown in the picture, for these 4 cases, the first one is the without cache tiering result, and the latency is about it's around 200 milliseconds. And then for the case 1, case 2, the response time is very good compared with the without cache tiering result. But for the case 3, the latency is huge. It is above 1,000 milliseconds. I think this is not acceptable.
Yep. Yes.
Yeah.
So so there's one thing that's just a cheap hack that might help with this. That there's a pull request or a branch that does this, but right now when we promote due to a read, so this would help the random read case. When we promote due to a read, it does the promotion first. It reads it from the backing pool, and then it writes it to the cache pool, and then it does the read. This patch will forward the read to the backing pool, and then promote. And so the first read, at least on that object, won't block at all, and only only like a second read to that same object that's right after it will block.
Are you talking about the promote on the second read patch?
No, it's actually different than that. It's once you decide to promote, it'll promote and it'll forward instead of promoting and then retrying the operation. And so I think in the random read case, it'll probably help a lot because you're usually going to touch that object once and then you're going to touch other objects. In other workloads where you have 2 reads to the same object, it'll only help with the first one, but the second one will be slower. But it'll at least pipeline them a little bit, so you'll have less of a penalty. But that'll help a little bit. But I think your point remains that promotion is expensive.
Yeah. Right.
Sort of
Yeah. Okay. In the next I did some latency breakdown data for the for the promotion, we divide this the whole time in the cache tier OSD. We divide into for the promotion, we divide into promotion copy and promotion replication, and then the total time is the cache tier OSD latency. As shown in the table, we can see for random read, when Q depth is 1, the promotion time is about 90%. It's above 90% of the total time. And for Q depth 16, it is above 50. For write, the time is even higher. For Q depth 1, and the promotion time is above 90%, 92%. And for write, for Q depth 16, it is above 76. So from this, we can see most of the time is spent on the promotion.
I mean, whenever you've got like a cache pool that has a lot of write amplification and you're doing reads, I mean, and you're doing over the network too, I mean, it's going to be expensive, right? I mean, that's just kind of the nature of this.
Okay, so that's true with this design. I think all of these slides are basically just saying cache misses are more expensive than they should be with this design, right? So that's true. It's a random the random distribution is actually a good way to measure the overhead of a cache miss.
Mm-hmm.
Yep.
Yeah.
So I mean, it seems like there are two directions to go, or two questions, or whatever. I think the first one is the thing that people care about isn't the cost of the cache miss, it's what's the actual performance impact on a real workload. And the thing that we keep running into is that all of the tools are terrible at sort of modeling a real workload, because they tend to write a bunch of new data, which is sort of a worst case for the cache, or they tend to usually do a random distribution, which is also a worst case for the cache. But a normal VM workload or whatever isn't a random distribution, and it's not just a big ingest operation. So it's a lot more work to set up the tests that actually sort of are realistic enough that they actually put you in a situation where the cache tier should help, or might help.
Sage,
I think that's part of it.
Even in situations though where we've got like a really skewed read-only distribution, we still see bad performance, even with like minimal promotions. So how bad are promotion?
Well, so yeah, so promotions, yeah, so promotions are bad, but you shouldn't. I think we should be careful about focusing just on promotion without also having some effort to look at what the actual impact on a more realistic workload is. And unfortunately, what more realistic means has been just hard to sort of figure out, because we don't have good models for what a typical what cloud VM workload looks like. What is the actual distribution? How skewed is a zip a good model, and how skewed is it? And how, because the key variables are whatever the zip parameter is, that is basically how skewed the distribution is to the hot data, and then the size of the cache relative to the base or the total data set. Like those are the two key variables, and there's obviously going to be some combinations that are good and bad, and you could ideally make a little graph that shows where it's going to be good and where it's not going to be good. But just being able to do that experiment would be helpful. But that's one direction, is just to understand. But then obviously the other direction is, yes, when you do promote, you want it to go as fast as possible, and it's expensive right now. So I think we sort of need to pay attention to both, if that makes sense.
Okay. As we talked in the email list, we also tested the promotion sync read result. Mm-hmm. This is a small feature we did before, and the picture two pictures shows that without when we have this feature, and then the IOPS improves about 2 times, from about 200 and 250 IOPS to about around 1800 IOPS, and the latency improves about 2-3 times, and improves about 60%.
Mm-hmm.
Yeah. Okay.
So I think this is a good example because if you really have a random workload, then you actually never want to promote ever. Like if your workload actually was random, then you would basically want to promote just a random subset, however big your cache is. Say your cache is 20% of your total size. You would just take a random 20% and promote it, and then never change the contents of your cache. That would be like the winning strategy. And so you would actually not want to promote on second read, but you want to promote on like the 100th read or something. So again, like, yes, it's great. Promote on second read is a really good idea and it helps, but the workload isn't the right one to show the situation where it's really going to help, and how much it really helps in the real situation is
actually
probably not
this. So 60%. when we do promote on second read, do we proxy it or not? No, we send a redirect back, right?
The first read we just redirect, and the second read we currently promote and then read, but with this new patch we'll redirect and promote in parallel.
Right. So I'm wondering whether the whole thing here is to see how many operations we can serve while the promote is going on. So we can serve reads in the general case while a promote is happening, right? By redirecting to the backend. If we want to make sure of ordering, all we have to do is proxy it, right? The read, that is.
Yeah.
Writes are a little trickier.
Even while it's as long as the promote is still in progress and no write has started, then we can tell them to redirect because the read is also in progress. So we could actually keep forwarding until the promote is done.
That's the trivial step one, I think. That if just promote on second read helps this much, then proxying reads during promote will probably help a lot. It'll probably turn your 20x overhead and latency on small reads down to something manageable. Slow, but manageable. Because you'll never block on a promote, right? For a read.
We can also so there are two. We can forward reads or we can proxy reads, and so far we've only been forwarding. So just being able to proxy reads in general will probably also have a sort of across the board improvement in latency. Although it'll cost some CPU on the cache tier OSDs, right? Because they're basically...
That's probably a reasonable trade-off for a 20-fold decrease in the 99th% latency, right?
Yeah, well, but it's going to be a trade-off that you want to make on a per cluster basis. It depends on...
No, I mean, it can be configurable, but I'm saying that seems like a choice many people will choose to make.
Yeah.
Writes are a little trickier. I think you're getting to that later in this talk, but we would need some kind of partial promote where we keep deltas of the object. That's harder.
I think that's where we're going, or where they're heading. But yeah, okay. All right, so I'm making a couple notes in the pad, but I think so. Step one would be the promote forward. Step two, or just a refinement of that, is to always forward when the promote is in progress. Actually, I should probably just change that theories to do that. And then a third step, which would be more complicated, would be to proxy the reads instead of redirecting the reads. But that'll be a little bit more code. Probably not too bad, but yeah, it'll be a little complicated. Sorry to interrupt. You can keep going.
Okay. Okay, and yeah, and this is the data I'm going to show, and then let's go back to the ideas. Okay, I will stop sharing.
Okay.
Wait. Okay. The first idea I'm going to propose is to use a fine-grained promotion unit. As we know, in the current Ceph, the default object size is 4 megabytes, and when we do promotions, we promote the whole object, and and I think that the 4 megabyte is too big for promotion. Thus, we promote to use a smaller promotion unit, and we can divide this object into 4K units, and we call each unit a page. And when we need to do promotion, we just promote the required pages. We do not promote the whole object. And we can use a bitmap to track the usage of the object. And
it's a solid idea in principle, but the interaction of that with snaps makes my head hurt. I'm also wondering how much of it you get for free just by proxying the read. Because keep in mind, even if you're promoting a 4K object, or a 4K page instead of a 4 megabyte object on a 4K read, you're still having the read wait behind the promote and commit, which is a network round trip and a disk operation. So you kind of still have to proxy the read. That's not optional.
Yeah, but we can cache this 4K page in the cache tier. So next time when we read this 4K page again, we just we can serve the request in the cache tier. We do not need to go back to the base tier.
So now we have to replicate a piece of the page cache too.
Yeah, right.
Also, how much read locality do you think most workloads have at the OSD level? That's my other question.
Sorry, how much what?
Like for RBD, for example, how much read locality do you think actually makes it all the way to the OSD?
I'm not sure about this.
I think you're duplicating the client's page cache if you do that.
Maybe.
This is a tricky issue, right? Because
lots of write locality survives, but I'm not sure a lot of read locality does.
Yeah, I think that the crummy part is that the read latency with promote, we can do these much simpler things that I think that will help a lot. Basically, proxying the reads and forwarding while we're promoting. And so I think there are simpler things we can do first that help with random reads a lot. But the random writes are the hard ones because we can't, in a simple way, either forward them while the promote is in progress or do them locally. And
I think you can. It's just hard.
It's just hard, yeah.
If there's no read in the transaction, then you can. Once you have the object info, you have a license to perform any writes you want, as long as you don't actually serve any reads. So you need to buffer all of the writes you haven't applied yet, and then once you continue to, what do? You forward the read, then overlay the bytes that have changed in the meantime on its way back. That's complicated. And then when the promote is complete, you have to apply the deltas to the new file, the new object.
I think the thing that worries me is that the way that promotion works right now with in a cache tier, during the promote, we're writing it to a temporary object, and it's going to be a series of reads, and only when we're done do we move it into place and actually complete the promotion. Whereas in this case, we need, in order to persist the client write, we have to have something that's permanently persisted that has enough data to overlay onto the object. So we have to have some. Yeah,
you could, for example, create an empty file and write to it just an empty representation of the file with the correct object info, and have the object info contain a
flag that says no content yet.
No, other way around. An interval set indicating which file ranges are correct.
Yeah.
Then when you complete the promote, you apply the deltas and then rename it into place.
Or alternatively, we would persist the write in a separate write aside thing that says these are transactions that we have persisted and will need to apply once the object is present.
I mean, that's pretty much what we're doing. It's just that we'd be doing it's per object instead of not per object.
Yeah, I'm just thinking how
that's the same thing.
How it would be implemented on the file store in XFS is going to be painful if we have to. rewrite the temporary file into a non-contiguous set of ranges.
Well, it's clone range followed by delete followed by copy. Or
instead of
rename.
Instead of a rename, which is what it is right now.
Well, it'll still be a rename at the end, but first it's a sequence of clone ranges, then a rename. You copy the extents over into the correctly copied object, then you rename it into place.
Got it. Okay. Yeah.
It's just very complicated. That's all.
Yes.
And again, if you try to serve a read in the meantime, you have to overlay those deltas on top of whatever you proxied back from the other guy.
Or
it breaks object classes too.
Yeah, I think probably any of those operations that are non-trivial partial writes, we would just block until promotion completes, unless and until we decide that that particular category of operation is so important and common that we should add the complexity to deal with it. And once you block one of those ops, then you have to block all ops, or at least from the same client. Yeah.
All the same object. Yeah.
Client per object, whatever. Yeah, it doesn't matter.
Right.
Okay.
The other thing is we can be more choosy about when we try to do the promote. Like if you do have a random workload, then there's no point in promoting ever.
Mm-hmm.
Right.
Yep. So we could forward writes too into the base tier.
Exactly.
We can't.
Right, you have to proxy.
We have to proxy writes. Yes.
Which is actually easy.
Right. So writes can be proxied.
That should interact. That should even interact correctly with snapshots without any effort at all. That's the kind of thing I like. Because we're sharing the snap IDs. They're the same. It should just work.
Yeah.
Random, possibly stupid question, but for promotions for reads, is there any reason that those objects need to go to a pool that's replicated versus writes that are coming in?
Sorry?
Say it again.
So right now, if you're doing a cache tier, you might use like 3x replication, right? So you've got a lot of array amplification when you promotion for a read. Is there any reason that you can't do something like separate out read promotions versus writes so that read promotions are going to some kind of pool that's not replicated?
No, because then if you write to the object, you have to move it over. I mean, you can get it, like if you happen to have that information a priori right now, all you have to do is configure your cache pool to be one replica.
And so actually this is a suggestion that somebody had in the read-only. This is total tangent, but to have a read-only cache where we promote on read, but if a write ever comes, we just delete it from the cache pool and then forward the write. And then the cache pool could be 1x replication. Because
that's actually a really good idea.
That's kind of something along the lines of what I was just thinking.
Read cache only. Yeah.
Some way to make it so that you can reduce the array amplification specifically for reads, and I don't know if there's something beyond that you can do, but
actually no, I'm not so sure because well, I mean, how many? Well, okay, so if you are using, okay, so RBD does not use, will pretty much never use an RBD or a cache pool for read caching. There'd be no point. It's got page caches all over the place. So RBD will always be a write caching situation, whereas Rados GW may genuinely be a read caching situation a lot of the time. And for a read caching situation, that might make sense.
Yep.
Presumably you may want it if you somehow think that your memory isn't enough, right? But I don't know.
I mean, maybe, but the difference in latency between page cache and an SSD cache pool is such that I doubt that an extra layer in the cache hierarchy is going to help that much.
Yeah, I kind of agree.
Okay, so sorry, coming back to your actual proposal, I think that the general feeling is that page granularity write caching is possible, and there are situations where it would help, but it's really hard. And this is my take, and there are a whole bunch of other things that we can do that are going to help a lot of the same cases that we should do first before we do the really hard thing. So I tried to make a list.
Okay. Okay.
So I basically, I think, yeah, I'll repeat. Yeah. So I think doing block or page granularity write caching is a good idea, and it would help for many situations, but it's also very hard and very complicated. And there are a bunch of simple things that we can do first that that'll also help, right? I tried to make a list of them in the pad. I don't know if the order makes sense if you want to look, Sam, but sorry, go ahead.
From our point of view, we think that use at the block or do promotion on the block or page granularity. We don't know. We don't think that it's too complicated. What is the complicated point?
Oh, of this, the interaction with. Oh my, the interaction with snapshots comes to mind as the most difficult. For one thing, you have to be able. So when you receive a read on an object that's in this partial state, let's say you're reading the first megabyte of the object and you've written random 4K chunks throughout that 1 megabyte piece. When you perform the read, the primary OSD will then have to perform the same read on its the part that's been promoted on the blocks that have been promoted, then overlay those results on top of each op that it proxied. So that's not impossible, but it's tricky. That's a thing we don't currently do. Object classes can't do asynchronous read, so that's a thing, but we can get around that by just not allowing it. Snapshots are tricky because you might receive a write with an updated snap ID while you're in this state. So you'll have a snapshotted partial object. So then when you finish the promote, well, let's say later when you go to write them out, you have to write out diffs, or if you chose to promote the whole object, you'd be promoting into an otherwise immutable snap. Oh, yeah, that's a thing. So clones are immutable currently, and we exploit that a lot. So if you only had parts of the clone written in, because that was the state it was in when you got the new snapshot, then now when you receive reads at other pieces of that clone, if you can't satisfy them, you either have to keep going to the cache pool, or if you chose to promote the whole object because it's really hot for some reason, you'd have to modify the clone when it's where it's sitting in the cache tier, which doesn't sound hard, but it surprisingly is. It's all doable. It's just.
Sam, assuming you could do all of this, is there any advantage to doing this relative to just using smaller object sizes in RBD from the get-go?
Yeah, there are other reasons not to use tiny objects. XFS doesn't really like tiny files. So 4K files are a good
idea. Is it possible that, for example, we have promote 4M object and we can, and the client OP is 4K read, and we can issue a promote OP, and we can get 4K target size, and then we can get 4M object data. So we can reply to client 4K data at first, and then fill 4M data in cache pool.
Sorry, I didn't quite get that.
The system has detected that a minimum number of lines are connected to this conference. Do you want to continue your meeting? Press 1 to confirm. If there is no response, the conference will end.
I think it's because we had people dialed in via intercall. They just need to hit the number 1 if you're dialed in by phone. But we are actually a few minutes over on this one.
Well,
do you want to keep going?
The next thing on the schedule was kind of the same thing.
Yeah.
Except much simpler. So.
Yeah.
Maybe one of the things we should talk about.
I made a few notes in the Etherpad on like the simplest possible approach for doing this, and I think that's to allow a partial object to be in the cache tier with a interval that says which ranges are written and a flag that says it's partial. And then if we get anything that isn't trivially satisfied, like a non-trivial write or a read that we don't have the full thing for, then we just fail. We either block and wait for a full promote or do another partial promote or whatever. And then we just have to, then the only thing you have to implement is the complexity of the partial object and the promote that sort of merges the two together. That seems to me like kind of the simplest thing. And then you can always add more onto like satisfy more complicated types of operations. But I think even with that sort of minimal strategy, I think these other things we should do first because they're way easier, and I think they're going to help a lot. And so that's the ability that's changing the read behavior to forward during the promote. That'll completely avoid the latency cost for promotions on read. I think it'll basically go away, right? And then also we can add the ability to proxy writes. So we have the choice not to promote on a single 4K write. We could wait until we have multiple writes on the object, like promote on second write type of thing. Right. And that would also, I think that would help. I think those are comparatively simple and will get us a lot of mileage with minimal effort.
Philosophically, I would argue that if we don't have 4 megabyte objects worth of locality, then promoting to the cache wasn't useful in the first place. Most of the time. So strategies where we hide the latency of the promotion, I think, will be more valuable than strategies where we promote less.
Okay. Should we look at the next? Do you want to look at the next one?
Yeah. Okay. Let's go to the next one. And the next one looks simpler than the previous one. Yeah.